Here's our first circuit on our breadboard. It involves two thermistors comparing temperatures to control a comparator. The first thermistor is measuring the heat from our heat source. The second one's comparing it to the room temperature. Each thermistor is creating a voltage divider. The first one with a 33K resistor, the second one with a potentiometer. This diagram shows a 50K potentiometer, but we use a 100K, which should be fine as long as we use the lower resistances. Each of the voltage dividers voltage goes into the comparator. When the heat source has heat on the first thermistor, it lowers the resistance, creating a higher voltage going into the comparator. When this voltage is higher than the room temperature one, it activates the comparator, allowing current to go through this leg. Instead of having an LED, this actually goes out to the output for our LED flasher.
The second half of the circuit we use is an LED flasher to emulate a siren. We use the output of the comparator as our 9-volt source. We used a potentiometer, 100 kiloohms and 1 kiloohm to adjust the signal output by the 555 timer, and the capacitor creates the oscillating frequencies. The 555 timer outputs to the transistor, which when high, it causes the current going through the transistor to increase. However, when we use this circuit directly, the LED in parallel did not have a high enough contrast, so we removed the 1 kilo ohm resistor as well as the 270 ohm resistor and placed the LED in the emitter portion of the transistor. This caused very little current to flow through the transistor until the 555 timer clicked up, and then the base of the transistor increased the current and the LED turns on. This is how we created the flasher. This is our breadboard. Power sources come into the breadboard here as to get the wires out of the way. The circuit begins coming through this black and white wire setup, which is the thermistor, which as you can see is connected to our robot, which comes in, and the thermistor is placed in front of the spray so that when it is heated up, the spray will put the fire out as well as cool down the thermistor as to not make the water continue to spray. Once the circuit goes through the thermistor, it then is measured into our lab jack as to create a plot of the voltage difference across the thermistor. The thermistor is put in series with the 33 kilo ohm resistor, as you can see here. This thermistor is the room temperature standard used to compare with in the 741 comparator here. The potentiometer we set and calibrated based on different temperature values, like lighting a match below it, and set it so that only when it is heated to a certain threshold will the comparator turn on. The comparator then outputs here to pin 6, and pin 6 then becomes the circuit for our LED flasher below. So the ground is the end of that leg of the infrared sensor, and the power is hooked up to the power over and the resistor of the original 741. The LED flasher works with a resistor going with a potentiometer in order to control the length of the pulses that the 555 timer outputs. The capacitor is used to control the frequency of the 555 timer. We altered the circuit, put the transistor in here as to increase the current when the clock is ticked up, and then this green and white wire here goes to our LED, which we placed as a lovely headlight to Lisa driving our engine, and when the robot is activated, the LED flashes. So our LabVIEW circuit here shows two plots. One is the voltage of the thermistor on top, and one shows the op-amp output and activation of it. So going to our block diagram on the left, the top half of the while loop is used to plot based on time for both of the values that we use or gather from the lab jack. The bottom half is the actual true-false statement that allows us to turn on or off the fire extinguisher mechanical instrument we have created. So what we have here is when this lab jack output is simply for the thermistor output that you see in this chart here. The second lab jack output measures the output of the comparator, and when the comparator, when the value the lab jack gathers drops below 7, this becomes true. It turns on an LED, which can be seen here, and the LED, when it's true, causes the motor of our NXT device to rotate 360 degrees, thus spraying. The while loop then runs again. We have the delay of a minute and a quarter, or 1 1/4 second, because the circuit must have enough time for the motor to run, because if the program runs again, it causes the motor to glitch out in regards to the distance it needs to be traveled. When the value becomes false, when the fire is extinguished, the motor then breaks and the circuit remains, thus not wasting any water. Now, as we can see over here from sample run, the op-amp has no current running through it, so the entire potential difference from the power source to the ground is remaining. And then once the once the comparator is flipped on, the voltage then is dropped over the resistor and the LED in the circuit, which is our LED flasher. And then once the fire is put out and the comparator turns off, the voltage returns to normal. So we will now show how our mechanism works. We'll start the LabVIEW program. This blanks our plots. Now when we come over here, the LED is off, as you can see right there. The mechanism is not running. Now when you light a fire and put it under the thermistor, you can light a match. It is quite helpful. Oh, look at that. So when the thermistor is heated, you can see the LED light up and then flash and then turn off. And you can see the drop in the voltage from the output of the op-amp, and then the spike in the voltage from the thermistor, because the resistance of the thermistor goes towards 0 as it's heated up to high temperatures.